Continuing on physical chemistry, chapter 19, section 3. We're talking about the hydrogen atom now. Notice the isotope, it's 1. So we have 1 proton, 1 electron, and 0 neutrons. Now, this makes it a 2-particle system. Now, hydrogen-like atom, or actually an ion because we got a positive charge, is any atom that only has 1 electron. So, hydrogen, monatomic obviously, or helium plus, lithium 2 plus, etc. Now this will behave like a hydrogen atom, except that you got more protons in the nucleus. So the attractive potential will be different between the 2 particles, the nucleus and the electron. Continuing on physical chemistry, chapter 19, section 3. So in a hydrogen or hydrogen-like atom, the potential energy is equal to minus Ze prime to E prime over R. So this Ze prime, this is the charge inside the nucleus, and this E prime is the charge of the electron. So Z remembers the atomic number, 1 for hydrogen, 2 for helium, and so on. Now E prime means we're going to be doing it in special units, like CGS units, to avoid constants. I'll explain why in a bit. And then R, of course, is the distance between the 2 particles, the radius of the atom or whatever. And then, okay, so we're going to be using CGS units to avoid constants. It'll just make the arithmetic a little bit easier. And like I said, the Ze prime, that's the charge in the nucleus. E prime is the charge of the electron. We have a minus sign out front because they have, this is a positive charge, this is a minus charge, so they're going to, the potential energy between them is attractive instead of repulsive. And then, so E prime is 4.80 times 10 to the negative 10 ESU, which is electrostatic units. Now, normally just E would be 1.60 times 10 to the negative 19 coulombs. That's the SI unit for electrical charge. And then ESU, that's called stat C or stat coulomb units, which is the same as Gaussian units. So here's our hydrogen-like atom. You have the nucleus in the center, so we have Z, the number of protons. And then you have the electron out here, and the distance between them is R. Continuing on physical chemistry, chapter 19, section 3. So the energy total of the system is the energy, the translational energy, the whole system moving as one, and then the energy from any internal motion, such as vibration and rotation. This is the same thing we talked about already in the previous chapter during particle in a box. Now for a hydrogen atom or hydrogen-like atom, the Hamiltonian for internal motion is minus h bar squared over 2 mu times the whole quantity, the second derivative with respect to x, second derivative with respect to y, second derivative with respect to z, minus z e prime squared over r. So remember r, just using the Pythagorean theorem twice, it's x squared plus y squared plus z squared, all that to the 1/2, the square root. And then of course mu is your reduced mass. The 2 particles is the electron and the nucleus, so that's what you use to find your reduced mass. So mu is equal to mass 1 times mass 2 over mass 1 plus mass 2. Now it doesn't matter which is which, so we arbitrarily said, okay, mass 2 is the mass of the electron, mass 1 would be the mass of the nucleus. Now remember, a proton weighs a lot more than an electron. It weighs about 1,836.15 times as much as an electron. So we plug those in here, simplify a bit, we get the reduced mass is equal to 1,836.15 times the mass of the electron squared, divided by 1,837 times the mass of an electron. That roughly comes out to 0.99946 times the mass of the electron. So obviously if you're only worried about a few significant digits, you can just round and say that the reduced mass is just the mass of the electron. Continuing on physical chemistry, chapter 19, section 3. So remember, the Hamiltonian of psi is equal to the energy times psi. That's your time-independent equation for energy of the system. Now, here's another way of looking at an atom. If the nucleus here, that's why I have plus Z times E. So Z is the atomic number and E is the charge, the proton. And then out here we have our electron, E prime. So remember we have x-axis, y-axis, z-axis. the angle from the z-axis is called theta, and then the angle from on the projection of the xy plane from the x-axis is phi, or phi, however you say that. So you take x, that's equal to r sine theta cosine phi, and y is equal to r sine theta sine phi. Z is equal to just r cosine theta. And of course, using the Pythagorean theorem twice, you get x squared plus y squared plus z squared is equal to r squared. Now remember, r can be anything from 0 to infinity. By using this system, theta can only be from 0 to pi. But then phi, you can totally rotate around, so that can be anything from 0 to 2 pi. Now let's talk about the complete wave function for the hydrogen atom. Now psi is going to be a function of radius and the theta and phi. So the radius, the function for that is capital R. It's a function of radius, but also two quantum numbers, n and l. And then for the angle theta, we have this function theta, which is a function of angle theta, and quantum numbers l and m. And then for the angle phi, or phi, we have the capital phi, which is a function of the angle phi, or phi, and then a quantum number n. So we have three different quantum numbers here, L, M, and n. These are the quantum numbers. Now A naught, remember, that's our Bohr radius. We're calling it just radius here for now, but we're going to talk about the Bohr radius in a bit. Now this part here, just based on the angles, we'll call that y for now. So that's the function of just L and m. N was for the radius. So that's just theta of Lm of theta times phi of phi, because there could have been an m here. This part's just called the spherical harmonics. So r is obviously a function of the radius, but what is this function r? Continue on Physical Chemistry, Chapter 19, Section 3. Well, here's the answer for that function of radius and quantum number n and l. So it's n minus l minus 1 factorial over 2n times n plus l factorial to the third power, all that to the 1/2, or square root, 2 over n times a naught, remember, so that's the Bohr radius, to the l plus 3/2 times r to the l, times e to the minus r over n times a naught, that's the Bohr radius again, times this function, capital L, from n plus l to 2l plus 1 of 2r over n a naught. This is called the associated Laguerre function. So each different atom or whatever is going to have a different Laguerre function. I think in the book there's a table of a few of those. So we have n equals, it can be 1, 2, 3, 4, etc. And then L, it can be 0, 1, 2, 3, 4, etc. But n can go all the way to infinity. L just goes to n minus 1. This is a necessary condition to keep this function well behaved. The Laguerre function, it's a polynomial. It's just a polynomial. Like I said, in the book there's a chart, you can look at that. And it's a degree of n minus L minus 1. Now, remember the position of our particle, there were three independent variables, the radius, the theta, and phi, in polar coordinate or spherical coordinates. So we have three quantum numbers, n, l, and m. Now m is actually ml, so that goes from minus l to l. So it can be 0 plus or minus 1 plus or minus 2 all the way to plus or minus l. So if l equals 1, then m can be plus 1, minus 1, or 0. Continue on Physical Chemistry, Chapter 19, Section 3. We're talking about a hydrogen atom. So we also have that function capital theta, a function of lowercase theta. That's equal to 2 times L plus 1 times L plus the absolute value of m factorial over 4 pi times L plus the absolute value of m factorial, all that to the square root, times p to the absolute value of m times x. Now this polynomial here, this p of to the m, that's the associated Legendre function. So as an example, p of 0 of x, that's 1. P to the 0 of x is equal to x, which remember, converting from spherical coordinates is cosine theta. And then p to the 1 of x, that's 1 minus x squared to the 1/2, which is converting from polar or spherical coordinates is sine theta. And then we also have that other function, phi of lowercase phi, the angle phi, function phi of angle phi. That's equal to a times e to the im phi. Remember, phi, lowercase phi is the angle, and then I is the square root of -1. So that's equal to 2 pi to the -1/2 times e to the im phi. Now, so we said before already, the hydrogen atom has 3 quantum numbers. We have n, which is 1, 2, 3, 4, all the way to infinity. And then we have L, which is 0, 1, 2, 3, 4 to n minus 1. And then we have m, which is plus or minus, or 0, plus or minus 1, plus or minus 2, all the way to plus or minus L. Continuing on physical chemistry, chapter 19, section 3. Now we're talking about a hydrogen-like atom, which remember I already said it means it has just 1 electron. So the energy is equal to minus z squared, remember z is the atomic number, over n squared, that's the atomic number, times e prime squared divided by 2a. Now a is h bar squared over mu e prime squared. Now remember, mu is the reduced mass between the nucleus and the electron. This comes out to be 0.5295 angstroms. So remember, E is the energy, that's the amount of energy the electron has. And then E prime squared, like I said, that's just the charge of the electron in the funny CGS units or whatever squared. Now remember, we said A naught is the Bohr radius, which is 0.5292 angstroms. So it comes out really close. But just to be consistent, if you're going to just round and say that mu is equal to the mass of the electron, then go ahead and use A naught, and we'll say we have rounding. Or, if we're going to actually calculate mu, then we'll use this, the actual A, and then you're not doing as much rounding. So it just depends on how much precision you want. I think for all the homework problems, you just do it with the approximation methods. So you'll notice then, the energy is proportional to 1 over n squared, or actually minus 1 over n squared. So it doesn't depend on the other 2 quantum numbers, n or L or m, just n. So we get degeneracy. So degeneracy is the result, energy depends only on n, but the actual psi function depends on n, L, and m. So what that tells you then is basically the energy of the electron, it depends on your radius, the distance from the nucleus, not on the angle. Continue on physical chemistry, chapter 19, section 3. So the lowest energy level, we say that's E1 sub 1. So there's 2 ways we can write that. We can write that as the 1s shell, or we just write it psi 100. There's no degeneracy in this state. This is the only state with that energy level. Now for the next energy level, we call that E2, there are 4 different states. There's the 2s shell, which we write psi 200. There's the 2p0 shell, which we write as psi 210. There's the 2p1 shell, which we write as 2,1 plus 1. And then we write, for the last shell, we have 2p minus 1 shell, which is psi 2,1 minus 1. So since these 4 different psi functions have the same energy level, we say this energy level is 4-fold degenerate, or has 4-fold degeneracy. Now the next energy level up, we call that E3, because n is equal to 3 now. And this one is, there are 9 different functions. So one we call it the 3s shell, that's written psi 300. There's 3p0, which is written psi 310. There's 3p1, which is psi 311. There's 3p minus 1, which is psi 31 minus 1. There's also the d shells now. 3d minus 2, so that's psi 32 minus 2. The 3d minus 1 shell, so that's psi 32 minus 1. The 3d0 shell, which is psi 320. And then there's the 3D1 shell, which is psi 321, and then the 3D2 shell, which is psi 322. That's 9 different states, all of which have the same quantum number 9 or 3. Therefore, it's energy level 3, but it's 9-fold degenerate now. So you probably figured out by now already that for any hydrogen-like atom, there is n² degeneracy. So for the next energy level E4, I would expect 16 different states. Now, if 2 states have the same energy level, it's because they have the same quantum number, principal quantum number, n. This is 1, 2, 3. But this is only true when you have 1 electron. When you have 2 electrons, the interaction gets rid of some of this degeneracy. Continuing on physical chemistry, chapter 9, section 3, we're still talking about hydrogen-like atoms. So we showed before the energy, how to find it. We had minus z squared over n squared times e prime squared over 2a. We substitute in for a. We showed before what that is. We get minus z squared over n squared times e prime to the 4th times me over h bar squared. So remember, z is the atomic number, n is the principal quantum number, e prime is the charge of the electron, me is the mass of the electron, and then of course h bar is Planck's constant divided by 2 pi. So we throw in all the numbers here except for z squared over n squared, and then we simplify. Remember, 1 joule is equal to 10 to the 7th ergs. So we get the energy for level n is really just dependent on 2 variables, your atomic number and then of course n. So we get minus z squared over n squared times 2.18 times 10 to the negative 11 ergs, or minus 2.18 times 10 to the negative 10 joules times z squared over n squared, or minus 13.6 electron volts times z squared over n squared. Now I kind of screwed up the scale here, but so we're graphing energy vertically increasing here against radius, of course. So at the lowest quantum number, the ground state, n equals 1, for hydrogen atom, that's minus 13.6 electron volts. For n equals 2, this should actually be way up here. I screwed up the scale. It'd be minus 3.4 electron volts. And n equals 3, it'd be squeezed in up here, that'd be minus 1.5 electron volts. I didn't draw this scale very well, but what you should be seeing is that it starts out pretty big and it's closer and closer and closer. As n approaches infinity, it's going to go asymptotically to 0. It's not going to get to 0. Continue on physical chemistry, chapter 19, section 3. So the potential depends on the radius. The potential, remember, is minus e prime squared over r. That's using CGS units. Now remember, it's negative because it's an attractive instead of repulsive. So the potential is equal to minus e squared over 4 pi e naught r if you're in SI units. This e naught is just for the purpose of getting units to work. It's called permittivity. And it's equal to 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Now, above 0 energy, think of that graph on the previous slide, the electron is, the amount of energy the electron can have is at any level. It's continuous. And that's because we're talking about a free electron. Now, below 0 energy, the electron energy is quantized. Remember, that's because the electron is bound to the atom. So you have to think more like the particle in the box scenario. Continue on physical chemistry, chapter 19, section 3. So now let's talk about ionization energy and ionization potential. So the absolute value of the energy in the ground state, that's the energy in the ground state. So that's the ionization energy. So for hydrogen, that's 13.6 electron volts. Because remember, we showed how in n equals 1 state, the electron is way down at minus 13.6 electron volts. So the ionization potential, we'd say that's minus 13.6 electron volts. Again, that's just for hydrogen atom. Now, let's talk about atomic units, or AU. This is another alternative to CGS or SI units. So the unit of energy is the Hartree, and that's equal to E prime squared over A naught. So we get 27.211 electron volts. And the unit of distance is the Bohr, which is defined as A naught. So that's equal to minus h bar squared times 4 pi e naught, epsilon naught, that's permittivity, divided by the mass of the electron divided by the charge of the electron squared. So that's equal to 0.5292 angstroms. So for hydrogen, we know that the energy of the ground state is minus 1/2 Hartree. Excuse me. Continue on physical chemistry, chapter 19, section 3. So we talked already about that function capital R of the radius and how it depends only on the radius. And for a hydrogen atom then, we have the R at the 1s shell, that's equal to 2 times z over a to the 3/2 times e to the minus z r over a. Or actually, this z, I guess it'd be a hydrogen-like atom. And remember, a is equal to h bar squared over mu e prime squared. So then the r function for the 2s shell would be 1 over the square root of 2 times z over a to the 3/2 times 1 minus zr over 2a times e to the minus zr over 2a. And then the r for the 2p shell would be 1 over the square root of 24 times z over a to the 5/2 times r times e to the minus zr over 2a. Now remember then, we also have the function theta of theta. So we have theta 0, 0, that's our theta s0. That's just 1 over the square root of 2. And then theta 1, 0, that means theta of p0. And that's just the square root of 6 over 2 times cosine theta. And then we also have theta 1, 1, which means theta p1, which is also equal to theta 1 minus 1, which is theta p minus 1. And those are equal to the square root of 3 over 2 times sine theta. Continue on physical chemistry, chapter 9, section 3. So here we've graphed a to the 3/2 times r of r against r divided by a, just to simplify. So notice the vertical axis just goes 0, 1, 2, and 0, 2, 4. So the nucleus is at r equals 0, obviously. So for a 1s shell, you get the highest value at the nucleus and then comes down. And then for a 2s shell, it also does that, but it comes down through 2, back up through 4, and back around. And then 2p, it starts at 0 and goes out this way. So you'll notice that for S shells, I showed the 1s shell and the 2s shell, that the R function at 0 is not 0. Now, this graph is misleading though, because keep in mind, I'm only showing the radius, but you have to realize we're talking about a sphere, not a circle. So think about what that means. So for S states, remember, L equals 0. So this function we talked about, y of L and M, it's equal to theta of theta times phi of phi. This is going to be constant. So remember we called y of L and M, that's our spherical harmonics. So for example, for 0, 0, that's just 1 over 4 pi. Continue on physical chemistry, chapter 19, section 3. So as an example, the psi 1s shell, so this is the psi function, wave function for the 1s shell. This is for a hydrogen-like atom. It's 1 over the square root of 4 pi times 2 times z over a to the 3/2 times e to the minus zr over a. You can pull out that 4 square and simplify. You get 1 over square root of pi times z over a to the 3/2 times e to the minus zr over a. And remember, a is h bar squared over mu e prime squared, where h bar is Planck's constant divided by 2 pi, and mu is the reduced mass, e prime is the electron charge, r is the radius, z is the atomic number. Okay, now you'll notice though, it's a function of r, just like I said, and there's no sine or cosine term. So what that means, that's because S shells are spheres. They're spherically symmetric. So there's no angles. S shells, though, of course, you probably already know this, they get bigger with higher n. This is not really to scale, but you get the idea. You have a 1s shell, and then a 2s shell, and then a 3s shell. Continuing on physical chemistry, chapter 19, section 3. So now we'll talk about molecular orbitals. So as an example, here's a sigma 2 pz orbital, or a pi 2 px orbital, or a pi 2 py orbital. All functions, wave functions, have nodes at the nucleus and infinity. That's basically your particle in the box condition. But we're going to ignore these when we're counting nodes. Those don't matter. That's just the boundary condition. So the number of actual nodes is going to be n minus 1. Now p orbitals have direction, but s orbitals don't. Remember we showed before, s orbitals are spheres. So what that means is the p wave functions, they're going to have the angles theta and phi in them, but the s orbitals did not. They just had r in them. Now, keep in mind though, we had this formula on the previous slide for r. And just the function r by itself, it doesn't give you probability of finding the particle anywhere. All it is, the orbital, like for S shell, is spherical. So, what we have to, well actually no, we're in spherical coordinates, that's what I mean. We're not talking about spherical order, we're talking about spherical coordinates. So we have 4 pi r squared times r of r. When we integrate that, we can find probability. Like when we want to find the probability of finding a particle here to there, we integrate from here to there and find out the probability. So the important thing is that even though the graph I showed you on the previous slide started out at the nucleus, you multiply this r squared, the nucleus r equals 0. So the probability is going to be equal to 0. So what that means is you're not going to find the electron in the nucleus of an atom.